Everyone. Today we're going to talk about another application to first-order differential equations, and that is population growth. Now, there have been quite a few different models related to population growth developed over the years. Today we're just going to talk about one particular phenomena that you learned about in high school in a rather roundabout way, and that is proportional growth. Alrighty. And so here's the idea. The idea is that the rate at which the population of some species grows is proportional to the population with respect to some proportionality constant. And so this proportionality constant is something that you would have had to compute in high school given this model. Like you wouldn't have been given the differential equation, but you would have been given something else that will look rather familiar here in a second. And so let's look at the solution to this model here on the next page. Okay, so we start with the derivative of the population with respect to time, the rate at which that population changes with respect to time, and we're going to solve this first-order separable differential equation. First things first, I separate the variables by dividing both sides by p and multiplying both sides by dt. And then I integrate both sides to get the natural logarithm of the absolute value of p is equal to kt plus c. Okay, and then I exponentiate both sides to get e to the power of kt plus c is equal to e to the power of the natural logarithm of the absolute value of p, which will lead me to p as a function of time, since p is our independent variable, our dependent variable in this case, sorry. And that is equal to e to the power of kt times e to the c. Then we redefine e to the c to be our arbitrary constant in front of e to the kt to arrive at this model. P of t is equal to c e to the kt. Now you've likely seen something like this before, because in high school it would have been modeled this way. And we'll show a little bit later on how that constant in front there is typically the same as the initial population given this model. And it'll typically make this kind of a motion on a graph as well. So there is nothing else impacting the population of the species other than the birth rates. So we're kind of neglecting a couple of things here in this model, but that's okay. We will get to that later on. Alrighty, let's go ahead and do an example. So it says here that a pond is stocked initially with 500 fish. Over 2 years, the population of fish in the pond reaches 750. And then the population of the fish is directly proportional to the rate at which the fish will be born. Then, assuming there are no environmental factors impacting the birth or death rate of the fish, and ignoring the impact of the fishermen on the dead fish in the population, how many fish will be in the pond after 16 years? And so, again, like I say, we're not going to pay attention to any factors that the amount of food the environment could sustain would impact on the fish or whatever, and we're not going to consider how many fishermen are in there and the impact that they have on the population of the fish or anything. We're just going to assume that the birth rate of the fish is the only thing impacting their population's growth. Okay, now obviously this isn't a very realistic model, but this is the most simple of the population growth models, and it's the one that we want to start with first because it kind of acts as a foundation for the next two. Alrighty, so what do we know based off of the problem that we just read? We know that the rate of the fish in the pond are directly proportional to the population of the fish in the pond. Okay, so we know that. We know that the initial population of the pond was about 500 fish. And then we know that we can compute some proportionality constant using this formula. K is equal to the natural logarithm of p divided by p naught over t. And you can just derive this formula coming from the solution that we found to the model earlier and isolating for k. Now, obviously, this model doesn't make sense to go ahead and use like the differential equation version if you have to go and compute the proportionality constant from the solution to the differential equation, which is why in most cases questions will give you this proportionality constant and you'll be asked to go from there using your separable differential equation regular methods. But for our cases, we were just given two different populations, and so we're just going to have them give us this formula. And then we also know that we need to ignore other factors in the problem. Okay. Alrighty, so we start off with our population model. We compute our proportionality constant by taking the initial population of 500 and having it divide into 750, which is the same as the natural logarithm of 75 over 50 divided by 2. So that's our proportionality constant, giving us this as our differential equation. Now, if we separate variables and integrate both sides, we're going to arrive at a solution very similar to the one we had before. The natural logarithm of the absolute value of p is equal to the ln of 75 over 50 divided by 2t plus c. And then if I exponentiate both sides, I'm going to be able to get rid of the natural logarithm on the left, which will leave me with just p of t is equal to e to the power of the natural logarithm of 75 over 50 over 2t times e to the c if I separate those exponents, since when we multiply exponents with like bases, we add the exponents. And then I'll bring that c out front like so, and apply my initial condition, which was that the pond was initially stocked with 500 fish. And now this is why it's clear that that constant is always going to represent the initial population, because when I plug in 0, e to the power of 0, or 75 over 50 to the power of 0 is still going to be 1. And so it's always going to be the case that when we have some initial population, that it'll cancel everything else out and we'll just be left with that constant. Okay, and then using the formula, p of t is equal to 500 times 75 over 50 raised to the power of t divided by 2. That's the equation that models our situation. And plugging in 16, we're going to get that we have a total of 12,814 fish expected in the pond after 16 years, as the question asked us. Okay. And this is what it would look like on a graph. So you can see right at the start here that we started about 500 fish, and then we start growing at an exponential rate, assuming there are no environmental factors impacting the amount of fish in the pond. And yeah, that's it. So in the next couple of videos, what we're going to do is we're going to discuss some of the more complicated population growth models that have been developed over the years. Hopefully this was helpful, though, to see the connection between some of the stuff that you've done in high school with some of the differential equation models which were behind the derivation of some of those pieces there. Examples of things you would have learned in high school would have been the half-life of a substance or the time it takes for a substance to double. Those are all things that are coming from this model of a differential equation. Alrighty, if you have any questions, feel free to email me. I have my email up on the screen right now. Otherwise, you're also welcome to send me a text, give me a call. Probably text me before you call me if you're going to go about that way. But yeah, I'll see you in the next video.